Thank you. Okay, we will start. So I'm Dr. Gopi from National Institute of Technology, Tiruchirappalli. Today what we are going to discuss is about machine learning for wireless communication. Basically what I am going to discuss today is the gap, right? I mean, you all familiar with many techniques and you studied the basics of wireless, right? And advanced topics in wireless, mathematical model behind it, all those things, all the stuff. What you really lag in general, right, this wireless group, is this machine learning knowledge, right? As I belongs to electronics and communication engineering, so I also know about what is in that wireless, right? So what are the topics involved in 5G, 6G, all those stuff, right? So what I am going to concentrate today and tomorrow is the various machine learning techniques which you must know as the basics, right? So that you can apply those techniques more comfortably, right, for the wireless applications, right? So it depends upon the requirement, right? So that is the goal, that is the objective of this, right? So we do the math, involved in math, machine learning, right? Some basic concepts, and then we do the MATLAB coding, right, related to that based on the theory what we are going to discuss, right? This will definitely helpful. This is going to be that we can say something like the foundations, right? So for this machine learning, right, topics, right? So in the morning, right, one of the slide depicts that the machine learning broadly we have three category, right? So one is supervised, unsupervised, and reinforcement learning, but it is not only limited to three, right? So you have still more, right? So generative models are there, right? Recursive networks are there, autoencoders are there, right? So of course we can put it in any one of this cluster, but still generative model is totally different. But we have lot of other models available in machine learning, right? So which we can actually explore. But of course the major cluster is this only, right? So you have supervised, unsupervised, and then reinforcement, right? So under the supervised morning, the same slide, right, says that you have what is called this dimensionality reduction techniques, and then you have a clustering algorithm, and then when it comes to this supervised, you have the deduction and then regression techniques, right? That's what we are going to discuss. In fact, this dimensionality reduction technique, we can say that it is in general, right? So it comes under the unsupervised, but we can even do dimensionality reduction with supervised also, like, right? So there is a small variation in that. Of course we cannot completely say that it is supervised as well as unsupervised, right? So dimensionality reduction technique is the common technique, right, which we can do as a supervised as well as unsupervised, depends upon the requirement. Basically dimension reduction should happen, that's all, right? So what is that we are going to discuss in this lecture, and followed by, so without this yeah, this is a book written by myself on pattern recognition and computational intelligence techniques using MATLAB, which may be helpful for you. You can recommend or purchase for your own use. So these are all the topics what we are going to cover. Dimensionality reduction technique. Under this dimensionality reduction technique, we are going to cover this principal component analysis, linear discriminant analysis, kernel linear discriminant analysis, and then kernel trick in kernel linear discriminant analysis. And then we go for this linear regression techniques, various regression techniques, and then logistic regression. If time permits, few more topics also we will cover, but these are all the main topics which is going to be that foundation for this machine learning. You have that pointer for change slide. Okay, so How many of you are aware of PCA, principal component analysis? We'll start with that. Fine, good. 2. Yeah. So what is that PCA from your point of view? Okay. 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 So what about yourself? Excellent, excellent, good. So, yeah, just for want of right cover with others, right? So both are right, the answers are right, right? See, actually, that's what exactly this PCA is going to do. But let me start with a basic definition of the dimensional reduction technique, right? So what does that mean? So it involves identifying the matrix A, right? So as you see here, U is a vector, A is a matrix, right? You need a matrix A that maps the outcomes of the random vector U to the outcomes of the random vector V, where the dimension of U is mentioned here as m cross 1, and then we have this dimension of V as n cross 1, and then n is much lesser than m, right? That is a basic requirement. Why really we need this dimension reduction, right? So we want to represent the data, right, with less number of features, right, by exploiting the redundant in that, right? So I will start with some intuition behind it. Let us consider this is a 3D space, right? You have the balls scattered in this room. Someone is saying, right, so I would want to represent this position of the balls inside this room, right? So obviously you can represent this one with what? 3 coordinates, right? X, Y, Z, the distance from this XY plane, YZ plane, and then ZX plane. So that is actually describes the position of the ball in this room. It's scattered here, right? So it is like that. But without knowing where the balls are actually, right? So you say that it is actually represented with what? 3 elements, right? But after entering this room, you are seeing these balls actually lying on the plane, for instance, right? So you can imagine the corner, that corner to this corner, have an imaginary. It is not exact. I mean, it's not actually the. I mean, uh, built plane, right? Something like that. It is a invisible one, but you are seeing that the balls are floating, right, like this, connecting that corner to this corner, right? So you have the balls floating on the 3D space. So what does it mean? Really, the ball's positions are represented with what? 3 coordinates, of course, right? It's a 3D. But after seeing that those position of the balls, we are able to understand that it is enough to represent those positions with what? Just 2 coordinate with reference to that plane. You got the point, right? So that is what we say, that some redundant, right? So here I'm saying just 3D to 2D, right? But reality it is all the way from something like 2500 to 13. See how much reduction, right? It's an arbitrary number I am telling, but imagine that much reduction is possible, even more, right? So it's all the way from 2500 to 13 is possible. So how to find out this redundant, right? So that there are many techniques, right? So we'll start with known technique, like the fundamental of all those things, right? PCA, principal component analysis. What actually it does? So you can see here, this is actually, I'm going to explain you with conversion from 2D to 1D, right? So this can be extended to 3D to 2D, and then even to what? 2500 to 13 dimensional space, right? So what you see here, this red and blue dots, right? As of now, this color information is not needed. That is needed for the next talk, LDA, linear discriminant analysis, right? As of now, you just see there are some dots, right? Represented with positions, right? So you have this red and blue points scattered on this 2D plane, right? Right. So all the points here is actually described by two element, right? X and Y. And now I look back to this data, right? You see that the data is varying in this direction. It is varying in this direction, right? So it is like this. It is varying in this direction. I am going to find out that direction. See, all the points whatever we are having, it is actually represented using what? The standard basis. I hope you all know that, right? So it is 1 0 and 0 1. It's the normal original coordinates, right? X and Y all are represented like that. Now what we are going to do here is we are going to find out the another coordinates, right? So it is like E1 and E2. They are all the different coordinate system now, right? So instead of representing the data with X and Y, you are going to represent the data with what? E1 and E2, where this E1, the direction of E1, you are actually going to identify in the direction of what? Maximum variance, where the data is actually varying more, right? So that direction we are actually finding out. In fact, as what's your name? Yeah, Venkat, right? Pardon? From where you are? Here, right? Good, nice. So as he mentioned rightly, right? So this is basically this eigenvector, right? So he said that we are going to represent the data with reference to the eigenbasis, right? So that's what, right? So this is the direction of maximum variance, and that direction happens to be the eigenvector. It is very easy to prove those things, and all we are not going to do, right? Using this Lagrangian multiplier, we can impose the constraint on the magnitude of this vector, and if we find out the eigenvector, I mean the vector that maximizes the direction, right, meaning the variance, right? So that happens to be the eigenvector, right? That satisfies this condition Cx v equal to lambda v, right? What is your doubt? No, E1, right? No, I don't confuse. I'll explain you, no problem. Right? See, actually, if I have a, for example, if I have the covariance matrix Cx, right, which is in the random vector x, right? If I have a transformation y equal to Ax, you tell me what is the covariance matrix of Cy? You have a random vector x, okay? That is having that covariance matrix Cx. You know covariance matrix, right? Now you have a transformation y equal to Ax. In fact, plus some mean can also be included, but that is arbitrary. I mean optional for you. Y equal to Ax plus b. Then what will happen to Cy? You are aware of this? Yeah, tell me what is that? No. Cy I need an expression. Okay, I'll tell you that. A Cx A transpose. Okay, this is the covariance matrix after applying the transformation. This is what y equal to Ax plus b, right? X is the random vector and you have the random vector y. They are related like this, y equal to Ax plus b. If that is the case, Cy is becoming what? A into Cx into A transpose. You got it? Now suppose that if my say for instance this x vector is of size 2 cross 1, 2D, right? And then you have this matrix A is of size 1 cross 2, right? So of course this B is going to be the scalar now, which is of size 1 cross 1 now, right? So now what will happen to this Cy? What will happen to Cy? It becomes a scalar, right? This is 1 cross 2, this is 2 cross 1, so automatically Cy will become 1 cross 1. Are you getting this? What is the elements of this covariance matrix? Diagonal wise, what is that you are having? Diagonal wise, it is going to have a variance of the individual elements. of the random vector, right? Are you getting this? So it is like sigma y1 square, sigma y2 square, they are all in the diagonal. Got it? Off diagonal you get what? The cross correlation. Expectation of y1 y2 minus mu y1 mu y2. You understand the point, right? So this is going to have the cross correlation, right? So it is like expectation of y1 y2 minus what? Mu y1 mu y2. And then 1 and 3, it is expectation of y1 y3 minus mu y1 mu y3. Understand the point, right? So what really, if it is diagonal, it means that they are uncorrelated. That's a different story, right? If it is 0, what is the meaning of it? The random variable which is actually available in the random vector, right? They are uncorrelated. You got the point, right? So now what I'm trying to say here is this vector is now 2 cross 1 and you have the matrix which is of size 1 cross 2, let us say, right? So then it is going to get what? Only one element. It becomes a scalar and that happens to be the variance. You got the point, right? So now the point here is, though I have written A as a matrix, now it is actually it is a vector now, right? So it is like this. This is of size 1 cross 2. This is of size what? 2 cross 1. B anyhow, it is, which is basically this 1D. You got this point, right? Right? So now I am imposing the constraint on what? E, this vector E. I am imposing the constraint on the vector E, right? So that happens to be, let me put it as like EHE having the magnitude 1, right? Lambda is a Lagrangian multiplier, right? And EHE, because you see that I want to, what is that our goal? I want to maximize this. After projection, I want to maximize the variance. You got the point? X is the vector in 2D. After projection, what is that you get? Scalar, which is of size 1 cross 1, right? And that covariance matrix, now it becomes simply what? The variance. I want to maximize that variance. You got the point? But if I am not imposing any constraints to this vector E, then I can choose any value for E that maximizes what? The scalar quantity, right? So there needs the condition to be imposed for the magnitude of E to control, because I am interested more on what? I am interested more on what? The direction, not on the magnitude, right? So I can put any magnitude. Here I have chosen that magnitude as what? EHE equal to 1, right? So if I differentiate this one with respect to the vector E and solve for it, you get, what happened? Yeah, you get what is given at the bottom, Cx V equal to lambda V, right? So what does it mean? This V becomes a eigenvector, right? Cx V equal to lambda V. So to answer your question, this is the direction of maximum variance after projection. Got it? Right? So projection means what? So let me tell you that one clearly. Projection means what? So let me tell you that one clearly. Right? So as let us consider this point. Only one point, right? So if I want to represent this one, with reference to what? The standard basis, what I have to do? I have to project this point. Say this point is x comma y, right? I have to project this point on the standard basis. Is it not? So this distance is going to be that x and this distance is going to be that y from this origin. If I have drawn with the proper coordinate, right? From the origin, the measurement is going to be what? X this direction and then y this direction. Basically, the coordinates what is available here, I have actually projected on the arbitrary line. But as I have chosen, this is the origin somewhere, right? This is 0. The exact coordinate axis are here, right? Right. So if I project some arbitrary vector on this standard basis, this is what we call it as a standard basis here. Can diagram on this, maybe this may be the origin, right? So that I can actually find out the distance, so that I can find out the actual coordinates x and y. I hope this is clear, x1 and y1. The distance from the origin, right? X and then y, that will be there. Now what I am going to do here is, I am going to project this one, the same point on the what? Eigenvector. Right? So it is like this. I am going to project it like this, and I am going to project it like this. You got the point, right? So I keep on projecting this, like, see, I keep on projecting this one here. So this is my projection on the eigenvector what? E1. Got it? It should be proper perpendicular projection. So just for want of time, I'm doing it faster. It is already there, some lines, right? So those are all the projections basically. If I project these points on the vector E1, right? So the points will be here, right? So these are all the points, right? So these are all the points, whatever the points you get here, these are all the projected points on the vector E1, right? I hope this is clear, right? So similarly, I can do what? The projection on this E2, for example, I can project like this, isn't it? Project like this, right? So I can project it like this, 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 right? So I'm doing a lot of projections like this, like this. So these are all the projection points on what? E2, right? So I get the same set of points. Points are the same, but when I project on the standard basis, I get the original data, right? Original representation 2D. But when I project that same data with using what? E1 and E2, we get a different coordinate values, right? Okay, what is the deal? I'm getting 2D to 2D, isn't it? So originally it was 2D. Sorry. Originally it was 2D. Now also it is 2D. What is the deal? Anybody? What is that advantage of representing the same data by projecting on E1, E2 rather than projecting on the standard coordinates? Any guess? Yourself? Okay. No, actually, yeah, variation means what? How far it is getting deviated, right? That's it. No, that's fine, but think about the after projection, what will happen to the range? I'm giving the hint. Huh? Huh? Which one? No. The proper word I used. Where? No, that's fine. But which? See, actually, I'm talking about this conversion from 2D to 1D. But what I am showing now, it is from 2D to 2D only, right? So now, what will happen to the range after doing this projection? That is the major point what I would like to tell you. I mean, if you know the range, see, for example, if I do this projection, see what is the corner, the extreme corner points here. See, for example, this is the extreme corner point as far as this the original coordinate axis is considered, right? This is the extreme points, let us say, and you have this as a range, right? So this is the range, right? You got the point what I am talking about, the range? The range is basically, if I keep on projecting on this axis, what is the minimum value and what is the maximum value I get, right? What is the minimum value and maximum value I get, right? So now here, this is my range. What is given in green is the range. when I project it on the standard basis, right? Okay, what is that range on the y-axis? Say, let us assume that this is the extreme points, right? So here I project this one to this point here, and maybe this point, right? So I project it here, right? So that you get a range here, right? So this is the range. So this is the range of the same points, right? Projecting on what? The y-axis. So you got this range 1 for the x-axis and range 2 for the y-axis. You remember this, what is that range, right? Now you see, if I do this projection on E1, what is that projection extreme point here? This may be the projection extreme point here, and this is going to be the projection extreme point here, right? So now let me use a different color here. Okay, maybe this, right? So this is my range, right, on this E1. Fine, until then is okay, you will not feel any interesting point up to this, but now you see this is the extreme point here, and maybe this one, I guess this may be the extreme point here, right? So now this is the range on E2. What do you say about the range of E2? E2 is getting reduced. In fact, the range of E2 even, see, this is only the picture what I have arbitrarily chosen, right? So it is fine, but you see that in practice, this range, right, whatever we project it on E1 is this much. I'm just telling in a scaling form, right, this much. And projecting on that E1 is like this, like this. The what I have shown in that black color is almost nil. Whatever I am showing that in yellow color, right, this range is going to be really large. That's what I said, maximum variance. That's what I said, it is a maximum variance you find this direction. The other direction, when you see that the distance is going to be, that range is going to be almost nil. In fact, we can simply ignore them, right? So it means that, what really it means that is, you don't want the eigenvector E2, I want only the eigenvector E1. It is enough for me to use this E1, right? So here the transformation matrix is just that E1 Hermitian if it is a complex data, right? And you have an arbitrary vector here which is of 2 cross 1, which converts into the scalar which is of size 1 cross 1. Right? So this eigenvector you have to choose corresponding to the maximum eigenvalue, the largest eigenvalue, right? So as this one is from this 2D to 1D, I'm saying you choose only one eigenvector corresponding to the significant eigenvalue, which is the largest one, right? But in practice, you are supposed to do it for the very large data, which is of size, let us say this X is of size, say 2500 cross 1, and you need to map, right? You need the transformation I said, right? So it is like that. And for the real, it is transpose, and if it is a complex, wherever I'm using transpose, make use of it, Hermitian transpose, right? So A transpose X, let me use real, A transpose X, and here this is going to be that size of 2500 cross 1, and this matrix Y, which is of size 13 cross 1, and this vector, I'm sorry, this matrix is of size 13 cross 2500, right? And this matrix A transpose, right, how you are going to construct it? You are going to construct by using that eigenvectors of the covariance matrix Cx computed using what? The outcomes of the random vector X. In fact, it is an estimate. You all know that, right? Covariance matrix, you know how it is defined, right? Expectation of X transpose minus mu X transpose, right? This is the way how it is defined. But to do this and all, we need density functions and all, right? But what normally we do is the estimate. I hope you know how to do this estimate, right? Take the vector, take the transpose, multiply, and keep on adding all those things. This is what actually we are going to do it in the program, right? So what actually, of course, we have an inbuilt function. We can use that. X1 transpose X1, X2 transpose X2. It goes like that, and then what? Xn transpose Xn and whole divided by n. This is going to be the estimate of the covariance matrix, right? So minus what? Mean. Mean, how will you find out? It is just x1 plus x2 and so on up to this xn, right, divided by n. The whole thing needs to be taken a transpose, and this term has to come here, right? So this is the expression for the estimate of the covariance matrix, right? Okay, once this covariance matrix is estimated, then we have to go for finding out these eigenvalues. And then if I find out these eigenvalues, if I arrange them in a decreasing order, right? So that's the surprising thing. That's what the main reason why this topic is relevant, right? See, actually your eigenvalues are drastically reduced, right, after few in real data, whatever you collect, right? So this is of 2500 eigenvalues you have, right? After 13 or 14, right? So the values are almost zero. 13 and 14 are arbitrary. I mean, in face images and all, it will be the 13 and 14. That's what I'm saying. For machine learning wireless also, we did some work with, for example, we did some work with the radar face image, right? So image collections using this radar signal, right? So in that, it comes around thousands, but the data length is huge, right? It's about 44,000 something. But after reducing using this PC, it comes under thousands also sometimes, right? So you cannot simply say that it is 13 or 14, but still reduce compared to 44,000 is fine for me, right? For representing the data, right? So it all depends upon how you are going to fix this threshold, how much you need to add these eigenvalues, and you have to say that 99% you need or 98% you need. Depends upon the number of eigenvalues you choose, you have as much number of reduction. Okay, fine. I hope this is clear for everyone, right? This is about PCA. So this one I will come back, right? Now we are going for that. Any questions up to this? Yeah. So the next topic, what we are going to discuss is it's the linear, there is spelling mistake, right? So linear discriminant analysis. Why this is needed? The same figure, right? What you see here, right? Now the color is needed for me, right? So now, as you know that sometimes you need to classify, right? So for example, the modulation technique, you want to know whether it is a QPSK or MSK, or right, you want to do that classification based on whatever the signal you receive, right? So somehow you're ready. This is the data with the two elements, right? So basically you collect the data, you want to represent it, right? So the raw data you are having, I am explaining everything with the two elements, but remember that this can be done for with higher dimension, right? So really high dimension, I mean, meaning the length is about thousands, right? So too big, right? So but I am explaining only with 2D, right? So everything I am explaining to with what, 2D to 1D, but it is true for the very high dimension to that lower dimension, right? That you have to keep in mind, right? Okay, now in this case, right, you have a label. What is that label you have? Red and blue. Red is of one modulation, let us say it's a modulation type 1, and then blue is of what? Modulation type 2, right? You need to classify. First of all, I have to represent the data. One objective in case of PCA is the only objective is just to reduce the number of features, right? To represent the data. It doesn't care about the label. It doesn't care about the label, whether it is a red or blue, doesn't matter. I just wanted to find out where that direction, right? Direction of maximum variance, and find out the eigenvectors, project it, and get the reduced data from 2D to 1D. That's what actually your PCA is doing, right? But now in case of LDA, you take care of this label, whether it is a red or blue. I have written here nicely that the after projection, how the covariance matrix is going to change, right? So now here in case of LDA, what we are going to do is we are going to use two scatter matrix. Scatter matrix is basically the covariance matrix, which is actually used the term in pattern recognition terminology. It is just the estimate of the covariance matrix only, right? So nothing more than that. We call that as a scatter matrix, right? So in case of PCA, we had only one scatter matrix, right? So it is basically the estimate of the covariance matrix, right? But in case of LDA, we are going to have two scatter matrix. One is between class scatter matrix, which is SB, and next one is this SW, which is within class scatter matrix, right? So what is the objective? The objective is still our interest is to what? Project to the lower dimension. Again, I go back to this original intuitive idea, right? So these balls are actually scattered on this room. I need to do this projection, right? What you normally do for the projection in case of PCA, your blues are there, reds are here. It's a 3D space, right? So some blues are there clustered there, and reds are here. What actually you did is you, from 3D I'm telling, right? So you actually identified the plane, right? And you placed the ball. See, even the ball are not available on that plane, you do small correction on it, means you push the ball, place it on the plane, right? That's what really we do, right? So you actually find out the invisible plane here, right? You have to find out the invisible plane here, right? So then you place the ball on that plane, right? So if suppose if balls are here, you place it on there. Just take the perpendicular movement of the ball and place it on the plane. And blues are there, again you do the projection and place it on the plane, so that you get, right, all the vectors available on the 2D plane, right? So this is from 3D to 2D map, right? Now what I am going to do here is, it is not only just projecting to the plane, right, to convert into 2D. Here our requirement is the blue, all the blues should come closer to each other after projection, right? After projection, I bring all the blue balls and come what? Make it come closer to each other, and all the reds to come closer to each other, right? So why that is needed? I need a proper discrimination, right? So if even after projection, right, see, basically for the classification, if I have a very good discrimination, classification becomes easy, right? So if some data both are looking almost same, then you will have always the dilemma, right, whether I have to declare this one with this or that, right? So there are many examples, like real-time examples, a dog versus cat. Some cat looks like a dog, some dog looks like a cat, right? Unless otherwise that dog gets exposed earlier, right? So we will sometimes say that it is a cat, but really it is going to be what? Dog, right? You understand? But if I represent this data with good discrimination, then your classification rate will increase, right? Sometimes, because whatever the data you collect with noise also, right, FSK or QPSK, for example, noisy data. So suppose that if the two types of modulation, two different modulation techniques almost end up with similar type of signal, then it will be not be proper to discriminate. So here the objective is not only to reduce the number of data, to get a better discrimination between the data, better discrimination between these data. So what really we do? What we do here is, we have to just the same example again, right? So I want to bring these blue balls to come closer to each other, and then red balls to come closer to each other. This is one goal. I have another goal. Another goal is, I want to make these blue balls separated from where? The red balls well apart. I want to make them apart, and the ball should come close to each other. So then it will be nice, right? So I will see blue balls here, red ball somewhere here. So very good discrimination, right? So I get some data, real data, and I project it in this space. So automatically what will happen, if it is FSK, this will get projected to this area, this region. And if it belongs to that modulation technique, it will project it to that region. So we can find out whether it is a red or blue, right? Very easily. Understood the point? Is it clear? Right? So that is the reason why we have two matrices, right? Between class scatter matrix and within class scatter matrix. Between class scatter matrix is responsible for separating the centroids, or otherwise mean of the individual class after projection. Everything we are talking only after projection, right? The earlier case, after projection, we wanted the variance to be maximum. Here also, after projection only. After projection, what is our goal? We wanted this mean of the individual classes to be apart, right? Understand the point, right? And the scatter matrix of the individuals. Individual means what? The blue as well as red. Individually, they have to come close to each other. Right? So for that, we have what is called within class scatter matrix. Right? So I explained this expression here. It's very simple. Let me start with this SW. SW, so here more general expression, this lowercase r is the number of classes. Right? So in that example, that value of r is 2. Right? Right? So that is r here. And what is nj? Nj is the number of vectors available in that particular class, right? So here it starts with j, right? So you have this nj here, right? So the number of vectors in the jth class is nj here, right? And this xij indicate this what? Ith vector in the jth class. You have total number of classes or what? R classes, and I indicate that ith vector in the jth class, and that is what your xij. And cj is nothing but the average. It is a mean of the individual class. cj, c1, c2, c3, and so on. We have, right? Or right. So that is that. Okay. So this is what within class scatter matrix, right? And you have between class scatter matrix. As I told you earlier, between class scatter matrix, what is that you have to use? You have to use the centroids of various classes, right? So you have this k equal to 1 to r. R is the number of classes. K is ranging from 1 to r here. And ck is the what? Centroid of the kth class, right? And c is the what? Centroid of the centroid. It is the mean of the mean, right? We calculated the mean of the individual cluster or class, and we have to find out mean of that, right? So what I'm telling here is like this. You have cluster 1, cluster 2, cluster 3, and you have this centroids available here, and you have to find out the centroids of the centroid. Somewhere here it will be there. That is C. This is going to be your C1, and this is C2, and this is C3, and then you have this mean over the mean, right? So this is what we call it as a C here. CKs are there, right? NKs are the number of vectors in the kth class as usual, right? So that will give you the between class scatter matrix. Okay, so what is the goal? The goal is what? You wanted after projection the centroids of various classes to be well apart, and then the vectors of the individual class to come close to each other, right? For that, what we have to do here is the objective function is like this, W transpose SBW, right? So this is the trace of W transpose SW W. I hope you know what is trace, right? So the summing up the value, right? The diagonal elements. Basically, after computing this W transpose SBW, what is there in the diagonal? We know what is there in the diagonal. It is nothing but a variance of the individual elements, right? So you wanted these variances of the individual elements after projection, right? Computed with what? All the vectors, right? To come close to each other. It means that that variance I want to minimize. Whatever is given in the denominator, that I want to minimize. And whatever is given in the numerator, that I want to maximize. So what is it overall, right? You have this numerator and denominator. Overall, I want to maximize this. This is my objective function, right? In case of PCA, what is the objective function? Trace of just W transpose SW, right? That's it. This is what you wanted to maximize. That is the objective function for PCA. In fact, we don't have SB, SW and all, right? It's only the total scatter matrix. That's it. Total, right? It is that overall data. It will not choose which class and all it belongs to, right? Overall data it calculates, and it wanted to maximize this. But here, this is going to be that. The solution for this one is similar to what we are had it for the PCA, is this SW inverse SB, right? Eigen vectors corresponding to the significant eigenvalues for the matrix SW inverse SB, right? So we can write something like this: SW inverse SB, V equal to what? Lambda V here. Otherwise, I can put it something like this: SBV equal to lambda what? SWV, right? So this can also be the way, because sometimes SW is not invertible, right? So, but essentially what we need to solve is this expression. This expression, we need to find out this V here, right? So, but understanding we are purpose, we can say that V is going to be what? Of course, it's true also, but SW need not be what? Invertible. In that case, we have to attack those problems and all, right? But still, V is going to be that eigenvector corresponding to the matrix SW inverse SB. Got it? So you have to find out that between class scatter matrix, within class scatter matrix, SB and SW, and you have to find out this SW inverse SB, and you have to find out these eigenvalues, arrange them in decreasing order, select the significant eigenvalues, and then the corresponding eigenvectors. Those eigenvectors, you arrange them to get a transformation matrix. Is it clear? So those eigenvectors you have to arrange, right? So like this, you have to arrange them to get a transformation matrix. Got it? Right? So that after getting this transformation matrix, it's very simple, right? As usual, you have this A transpose X, which converts the vector from the higher dimension to the lower dimension. V, yeah, V is the eigenvectors. This one you are talking about, this V. Yeah, yeah. No, no, this is by definition. What is eigenvector basically? I mean, yeah, that's what I have written. So in place of the matrix, here we are having SW inverse SPH. Yes, eigenvectors corresponding to SW inverse SB. That is what we are collecting. It is not single vector, right? I can have multiple vectors for it, satisfying this. This is V1 here. In general, I can put it as Vi. It is not going to be that single vector, right? I can get V1, V2, V3, depends upon, of course, I have to put the corresponding lambda I here, right? So for the lambda I, for the eigenvalue lambda I, you get the corresponding eigenvector, right? For lambda 1, you get the vector V1, got it? So lambda 2, you get a vector V2, and so on, right? But you are going to select only the significant eigenvalues, got it? Dimension wise, if I want to explain, it's very simple only, right? So let me consider that the vector size is of size what, 2500 cross 1. So what is the size of SB? What is the size of SB? It is going to be what? 2500 cross 2500, right? Because what is the size of CK? Size of CK is a centroid, right? So it is 2500 cross 1, right? So when I take transpose, you get what? 1 cross 2500, right? So I made some mistake here. This is supposed to be after transpose, it is actually 2500 cross 1, okay, right? So sorry, so this is 2500 cross 1 after taking the transpose, okay? So what I mean by that is CK is you have to take the transpose here, that's the thing, okay? So SB is of size 2500 cross 1, 2500 cross 2500, and SW is also having the size of 2500 cross 2500. In fact, here also I think I made a mistake. Here transpose should come here. This is 2500 cross 1, right? XX transpose, that's the way how we did in PCA, right? The same thing only. Xij minus Cj into Xij minus Cj, the whole transpose. Is it clear? You're from which place? Here, Patna, okay, NIT Patna. Right? Any other questions up to this? I would like to reply for that. Any doubts, sir? Okay. Reish, or I'm not getting you. Yeah. Yes. Yeah, you are summarizing. Okay. SW inverse SB, right? Yes, yes. What he said is yeah, eigenvalue, and then you have to find out the eigenvector corresponding to the significant eigenvalues, right? So those things you are going to arrange them in a column wise, right? So for example, if I selected 13 eigenvectors, right? So individually they are going to have the size of 2500 cross 1. So the total matrix size is going to be 2500 cross 13. So you have a projection, right? A transpose X. X is of size 2500 cross 1, and this is going to be of size 13 cross 2500, and you get this one as 13 cross 1. I'm using transpose here. If the vector is of the complex, right, then you have to go for the Hermitian, right? So that you know. Okay. So any other questions? Is it clear? So see, yeah. Okay, okay, it's Y. So don't. These are all the obvious things, right? Okay. Right? Any other question? Yeah. Yeah, please. You have any questions, madam? Yeah. Excellent question. In fact, that is the next topic. Right, that is the next topic. Actually, what I thought of discussing. Actually, right, the topic is actually PCA versus LDA. Right? Is it coming through the speaker, or I'm shouting? Don't know, because I will get energy lost now. Yeah, now it is fine. Yeah, because I don't know, but when I hear the sound through the speaker, I feel that you are all getting. Otherwise, I will shout. That's my habit. Right. Usually in the class, when we use this thing, I check whether it is coming through the speaker. I mean, when I hear, right? So then I can reduce my right energy. Yes, I can efficiently use, because I am worried, right, whether it is reaching you or not and all. Right? So but it is very low earlier. Okay, right now I think it is better, right? So now, yeah, this you are from which place, madam? Okay. So the question is the very important and excellent question. Actually, this PCA versus not KLDA. KLDA will come later on, right? PCA versus LDA. There is a paper, in fact, on IEEE transactions on pattern analysis and machine intelligence. The paper title itself is PCA versus LDA. Right? So that's a good paper. You can actually go through that paper. Basically, to summarize that paper, that finally, right? So we cannot actually claim that LDA is always better than PCA. That's the final answer for to that. The reason is actually, in fact, it looks, based on whatever I told earlier, right? Intuitively you may think that LDA is doing better, it is bringing all the vectors closer here, this, that, and also LDA should work better, right? But the point here is, the whatever given the data, right, if it is sufficient, right, more number of data, then LDA will definitely do better, no doubt in it. But unfortunately, the data, whatever we are having, right, that is not sufficient to describe the complete information about that cluster, right? So in that case, right, so even when I try to bring all the vectors and all, right, so for example, this is the example what is given in that paper particularly. So here we expect the circles to be available in this ellipse. These are all the contours of Gaussian, right? So we expect 2D, right? So these are all the vectors to be there for this class, and we have this cross, right? So to be available in this case, right? But we have only 2 circles and 2 cross given to you. The data is very limited, right? So if I have more number of circles and then more number of cross available, then if I do this LDA, it does the job nicely. But when I have only this 2 circles and 2 cross like this, LDA sometimes misguide, it becomes overlap. See, actually, when to say that it is inferior? After projection, we say that it is inferior, right? So how, when to say that, how to say that? It is actually, we can tell only if you get overlapping. After projection, I don't want this red and blue to get overlap. If it is well separated, right? The objective function we are actually constructing, but still after doing projection, we feel that the data gets what? Overlapped. In case of LDA, but in the same case, when I use PCA, there is no overlap, right? For instance, this case, this is the direction of maximum variance. If I project this data here, right? So 2 crosses will be here and 2 circles will be here. They are well separated, right? So if I construct this LDA and if I project, then you get what? It looks like, let me see. The main point here I want to tell you here is, you are doing this job only with what? Training data. Whatever is given to you. For the training data, it works very nicely. See, I told that you want to bring the red balls to come closer to each other, blue balls to come closer to each other, right? Like that. And what are those balls? And these are all the training data. It works nice, right? So we brought the training data to come closer to each other. But do you think that only the vectors will be around that region? In reality, we don't know, because the data are insufficient. You already brought it. So I am saying after projection, it should like here and there, it is like there. But you have a new data coming. When I do this projection, that's red or blue, we don't know, right? I cannot guarantee this red will come to this red, and this is, if it is a blue, it will go to that blue. No, we can't say, right? The transformation matrix we cannot 100% say that it will be the proper projection, right? It works nicely for training, because that's subjective, right? So our objective is to bring the vectors to come close to each other. That is, the objective is meant for the training data. So for the training data, it works nicely. You will be happy, yeah, it has done. But when you use this testing data, overlap occurs. So when we are using this testing data and you see how the data are working after projection, then only we can conclude whether it is PCA is based or LDA is based and all, right? So unfortunately, we can visualize 2D, 3D, but when I do it in the reality, we have to play with what? Very high dimension, right? So for that, we visualize only using some matrix like what is called this distance matrix. You see here, this is what normally we use, how the data are available in the higher dimension space. Just to see, right, how the vectors are arranged. What we really do is very simple. Concept is very simple. We find out the equivalent distance between all possible combinations, right? So it is like, say, in this case, there are 350 vectors, right? We find the distance between the vector v1 with v1, v1 with v1 with v2, right? It goes all the way up to this v1 with v350, right? And then again v2 with v1, then v2 with v2, and so on, right? So we arrange them in a matrix form. So when you see this black here, the distance is almost 0, meaning those vectors are closer. Whenever having a different gray shade, right? So it is having a very separation, in good separation between this. You see that we call this a block diagonal, right? Block diagonal matrix like this, right? So it means that this is this belongs to one class, this belongs to the second class, this belongs to the third class, this belongs to the fourth class, 5, 6, 7, 8, 9, and then 10. There are 10 classes here actually. Not every classes are very close to each other, right? So this is good, these two are good, this also okay, this is not that much good, this is not good, these two are not really good, right? Like that. This is what how we visualize, and if we want to say that it has done a proper job for the testing data, I repeat, right? Training data normally does the job proper. For the testing data, if I compute this distance matrix, if I am getting a proper block diagonal, all that diagonal is going to be that pure zeros, and then off diagonals are going to be that very high value, then it will work in a real situation. Until then, we need to do a proper training for the dimensionality reduction. I hope this is clear. And we go for the next topic, which is KLDA, right? All the colors, when I talk about the color, automatically what does it mean? I'm talking about some index available, right? So, see, the moment when I say color, there is some index in it. So when I am, see, then I will not use the term color there, right? I will simply say ball. I don't worry about that color. So in that case, I simply say balls, that's all. The moment when I say red ball, blue ball, then automatically what does it mean? I mean, I already labeled them, right? So I had a class label over it, right? So in that case, it is just a ball for me. It is like that. Another very, very interesting, this one is what I love, and this machine learning techniques, right? Many of the techniques, they use this kernel trick, right? So I'll put something like that, because this is the one which makes machine learning very interesting, right? Because if I do with the data, the raw data, whatever we use, and we play with that, it will not work. But we are still able to apply this one in many applications successfully because of what is called this kernel trick. What is that about? See, actually, I told that this is red ball, blue ball. Safely, I made it as these vectors are right well separated. Blues are here, reds are here, like that, right? So let me give you one example like this. This is red, right? In reality, right? So of course, it is again, it is 2D data only. This is 2D data, right? But you see that the class 2 is available like this, right? They have a boundary. In fact, they have a boundary, but it is not like what you had it earlier, right? A proper linear separation. If it is a 2D, we say that very good separation is happening with a line. In 3D, plane, right, which separates this to a group of vectors. But this type of data is what actually available in reality in case, right? So here, there is no line which can divide these two classes. Linear separation is not possible in this case, right? So most of the final classification in the sense you do projections and all, but further that is only dimensional reduction, right, which facilitate for the classification. After that, we have many techniques for the classification, like support vector machine is there, nearest mean technique is there, logistic regression is there, so many other techniques. Neural network is that. Neural network, normally we don't do any pre-processing thing, but still, after performing the dimensional reduction only, we go for a actual classification. For performing the classification, the main requirement is a good linear separation between the class. As I told you earlier, so you need this red to be here and then green to be here like this. And I need a line that separates these two nicely, okay, right, like this. But unfortunately, the data are something like this, right? So what to do? So the idea is actually you are going to map these vectors to the higher dimension. This I am giving the example with what 2D, but reality, you see, if you are having a data with 2500, you still map to the higher dimension. You still map to the higher dimension. Why we do? We get a good separation. What is the intuitive behind it? Very simple. I'll say that same example if you are given, right? You see that the red crosses are there, right? Let us assume that the red crosses are coming out of this screen. Let me see here, right? So this is 2D data, right? So you project this red cross to bring out of the screen perpendicular projection onto this space, so that the 2D becomes what? 3D. In 3D, reds are here and greens are on the board. You see that there exists a plane that separates this into two. Got the point? Right? See, in 2D, I am not able to find out the line that separates into two class, but when I project this vector to this 3D, I'm able to find out the plane that divides this into two class. That's the interesting point. Okay, fine. What is a delineate? I mean, in fact, in practice, what is the dimension I have to map and all is the question mark, right? And that is where this kernel trick is coming into picture, where we don't really map to the higher dimension. That is the interesting point. I said we need to map to the higher dimension, but it doesn't really map. See, because if I want to map to the higher dimension, I need a function called phi, right? So you have a vector x, and then I apply this function x, and then I can convert this vector y, which maps this vector to the higher dimension, right? And finding out this function is the question mark, and what is the dimensional change I have to do, that is the question mark. There are things, right? So now the kernel trick is actually most of the techniques, including KLDA, because kernel trick is a general story. The kernel trick is used in SVM also, right? Kernel trick is used in many places in machine learning algorithm, right? So wherever this kernel trick is, in regression also it is available, right? So the kernel trick, wherever you are using this kernel trick, the idea is in the expression, right? You have the expression like this, which is basically the inner product of two vectors in the higher dimensional space. Phi of x1 is a vector in the higher dimensional space. Phi of x2 is in the higher dimensional space, right? And you are doing the inner product of that, right? And this inner product, you are going to call that as the kernel function. I don't want phi anymore. I don't want this, but I want this. This is the kernel trick. We don't, because in the derivation, right, when you find out the linear plane that separates the two class, right, in higher dimension we call it as a hyperplane, right? So in 2D it is a line, and then 3D it is a plane, and then if you still move to the higher dimension, we call that as a hyperplane. That is the ultimate goal. We need to find out this hyperplane which that divides that clusters into or classes into two parts or multiple classes we are having. Like between the two clusters, we need to find out the plane, hyperplane, right? So for that, to map the vectors to the high dimension, I need a function called phi, right? So instead of using explicitly the function phi, what we do here is we define what is called the kernel function, K. The kernel function is defined on the vectors which is in the feature dimension space. I mean, your data, whatever is given, x1, x2 is the data given to you, right? It's in the feature dimension space, right? So you apply this kernel function to these vectors to get the inner product in the higher dimension, right? And while solving the hyperplane, right, in whatever the application behind it, right? So wherever we need the inner product to be computed in the higher dimension, everywhere we replace this one with the kernel function, right? So suppose if you have already had an experience on working with SVM, anybody had experience on working with SVM, support vector machine? Support vector machine, you are aware of support vector machine? Support vector machine, no one has any other machine learning algorithms used using MATLAB and neural network, even neural network also, right? So, but neural network by default, it is there already inside it, right? So, but when you go for the SVM, for example, toolbox, if you have a toolbox in SVM, there is one parameter called the kernel function to be chosen, like the Gaussian kernel function, right? Like that. So if you go for that linear regression, again we need to choose this kernel functions, like polynomial kernel function. Again, popular is Gaussian kernel function, trigonometric kernel functions, all those things, right? So these kernel functions are basically defined on the vectors in the feature dimension space, which computes the inner product in the higher dimension space. But how that is going to be helpful, right? So that one I can explain you actually for what is called this KLDA. Now you know what is LDA, right? So the LDA performed with the vectors in the higher dimension space is what we call it as KLDA, but we are not going to really map the vectors to the higher dimension space. That is the trick, right? So that is that KLDA here. Yeah, this is that. This is slightly, yeah, I can go for that. Okay, any doubt up to this? Okay, right. So now you see that carefully, it's simple only, but you have to clearly understand that. So, okay, right. So you have this vector u, which is in the future dimension space. You are going to map to the higher dimension space as I told you earlier, right? So using that function phi of u, which is v here, right? And this v and this v are not same, right? So don't, maybe I can change this variable to z. Right, this is the z, right? So this is the vector which is in the higher dimensional space, and using the vectors in the higher dimensional space, right? So what is given to you is these vectors u1, u2, and so on, right? Like say for example n vectors. These are all the vectors given to you. Got it? So these are the vectors. Of course, you have the index also. Vector which belongs to which class also is given, but for simplicity, I'm simply naming all the vectors without the label. As madam told, right? I mean, red and blue. Now I am calling it as a ball only, right? So, but we know whether it is a red and blue, it is available. I don't want to confuse, with double subscript in it. So I am simply calling these are all the balls. That's all, right? All the vectors are there, but class labels are available. Class labels are available. I know which U's are red, which U's are blue, which U's are green, everything I know. Right? So that is, but I am simply calling this a number like 1, 2, 3, 4, 5, and so on up to this n. It is given like that, right? So now you are going to map this vector to the higher dimension space using the transformation u. I said you don't want phi, right? Right? Yeah, that will come little later, right? Now I am starting with what? Phi, right? So later on we will realize that phi is not really needed. We need only k. So that point it will come, right? So now here we are having this v equal to what? Phi of u, which maps the vectors to the higher dimension space, not lower dimension space, right? So v is in the higher dimension space, right? Now see the corresponding vectors, let us say the corresponding vectors are v1, v2, and so on up to this vn. They are all the vectors in the higher dimension space. Got it, right? Using this vector, I can find out, right? So I know the label. So I can find out what? Between class scatter matrix, and then what? Within class scatter matrix, like just like what we did it for this LDA, right? So those vectors are this. Those vectors are this. Those matrices are this. Between class scatter matrix and then within class scatter matrix, right? And you know that Z is the eigenvector satisfying this, right? SW inverse SB. I am calling it as SWV inverse SWV, right? Z. So this is what I am interested on. So my interest is to get this Z, the eigenvectors in the higher dimensional space. That's what really we need, right? Once you get Z, what you will do? If I have a vector Z, only one vector if I am computing, only one eigenvector if I am computing, Z. So what is that I do? Z transpose, right? So you are given a vector, some arbitrary vector, let us say U test. This is the vector given, feature vector given. What are the steps you need to do? We have to first use that function phi to get what? V test, right? Using that function what? Phi, right? We don't want phi. I will come to that one later on. But if you are having phi, what you do, right? So you are given U test. I use this function phi to get what? V test, right? So how they are related? V test is simply phi of U test, right? Right? So then what I do? I got an eigenvector for it. I simply multiply this one with what? V test, right? Otherwise, it is nothing but phi of U test. This is what actually I wanted to do. But finally, what is our requirement is to find out Z. It is not this one I have chosen only one vector, Z. That's what I have chosen, Z transpose, right? But you can have multiple eigenvectors also, right? So this is just for converting into 1D. Whatever the dimension you are having, now this does the job of converting into just 1D. I have chosen only one eigenvalue. But it is, we can extend this one for what? 2 eigenvalue, 3 eigenvalue, depends upon the significant number of eigenvalues, we can do it. But ultimately our requirement is to find out what? Z. You got this, right? Now this is the key point here, right? This is the thing, right? So here, this eigenvector Z, right? This is the eigenvector, which is basically computed using this between class scatter matrix, and within class scatter matrix is computed using the vectors in the higher dimensional space. Got it? So that eigenvector can be represented as the column space of the vectors used for constructing this between class scatter matrix and within class scatter matrix. What I really mean by that is, if I have a matrix M, this is a matrix M, I'm constructing that, and here these individual vectors, right? V1, V2, V3 and so on are there. They are basically what? Phi of U1, phi of U2, it goes all the way up to what? Phi of UN, right? What I am saying here is, this eigenvector Z can be represented as the linear combination of these vectors, right? Pictorically, I will explain it in a different way. I mean, this will really make you very clear. What I am talking here is, you have the vector space. I hope you know what is vector space and all. This is the vector space, right? And individually, these vectors are, let me say, that is phi of U1, phi of U2, like that, right? So let me call this as phi of U1, UN, right? These are all the vectors in the vector space. The linear combination of these vectors forms the vector space now. This is a spanning set. You get a vector space now, right? The claim is, this eigenvector Z, right, which actually lies in this space. So very simple. Intuitively also we can understand, but this is the thing, right? So what does it mean is, there exists a vector called U that relates what? Z equal to MU. You got it? Z is the, what is Z? Z is the eigenvector in the higher dimensional space. The vector Z, which is in the higher dimensional space, can be represented as the linear combination of these vectors, that is phi of U1, phi of U2, phi of U3 and so on, right? And let us say the constant is alpha 1 phi of U1 plus alpha 2 phi of U2. It goes like that, and then alpha n phi of UN, right? And these alphas in a column form like this, phi n, and that vector is U. Okay, now you got it, right? I hope this is clear, right? Any doubt you can ask. Is it clear? Right? So I'm making it as simple as possible, right? Is it clear, right? So the vector vector Z, right, can be represented as the linear combination of the vectors in the higher dimensional space. That is phi of u1, phi of u2, and so on up to this phi of un, right? So you get that coefficients alpha 1, alpha 2, and so on, right? That. So this is the starting point for this kernel trick, right? So you can see that this is z, this is z, z is mu. So from this expression, you are getting that SBV in place of z, I am replacing with what? Mu here, and this SW V, right? That I am writing as it is, and then this vector Z, again I am writing it as what? Mu, right? And now you are simply multiplying on both sides with what? M transpose, right? So now this is M transpose SBVM, and this is M transpose SWVM, right? Got it? So now you are getting a new between class scatter matrix and within class scatter matrix, right? Up to this, any doubt? What is the goal? Our goal is to find out Z. The trick is, first I'll tell you the trick and then I'll go for the math. The trick is, instead of getting this Z, we are going to get directly this U. We are going to get directly this U, right? We get this U and then we get what? Z. Okay. Computing U is very straightforward now. It is going to happen in a straightforward method now. How? So you up to this is clear, right? Any doubt in this? Right? Now this, you consider this matrix, right? You consider this matrix here. This is the inner product. V1 transpose V1 is the inner product, right? So what is V1? V1 is basically phi of U1, right? You have this U1 in the feature dimensional space, right? Which maps the higher dimensional space, which is actually V1, using the function phi, right? Clear? Right? So then this V1 transpose V1 is actually phi of U1 transpose into what? Phi of U1. This is the place where we are going to replace this phi of inner product, right? This is the inner product in the higher dimensional space. This one we are going to replace with what? K of U1 comma U1. Using that kernel function. Okay, fine. I can of course replace this one with the kernel functions now, right? But what is the deal? The deal is, if I construct this matrix, right? What is the size of this matrix? The size of this matrix is going to be that n cross 1. Let us take an example, very simple example, like only two class 1 and then class 2, right? And here you are going to have this vectors like u1, u2, u3 alone, and this one let us consider just u4 and u5, just two vectors for understanding purpose, right? So like this, and these vectors now we have converted into the higher dimension. So u1 is becoming v1, u2 is becoming v2, u3 is becoming v3 using the function phi, right? So it is like that. u4 is converting back to this v4, and then u5 is converting back to v5 here, right? So now what is the size of this inner product matrix? I am having only 5 vectors, right? So this capital N is going to be that 5, right? So this matrix, as far as this example is considered, it is just what? 5 cross 5, right? Because capital N is what? 5 only. This is just 5 cross 5. The important claim is the first 3 columns of these matrices, the first 3 columns of these matrices are treated as the new vectors belonging to class 1. The first 3 column vectors of this matrix, right, belongs to class 1. And the next 2, the remaining 2 columns, right? Next 2 columns can be treated as a vector belonging to the class 2, right? Using these new 3 vectors and 2 vectors, I can comfortably compute between class scatter matrix, within class scatter matrix. You know how to do it. That formula is already there, right? And those between class scatter matrix and within class scatter matrix are these things, or this one, right? M transpose SPV M transpose SWV M. They are all the between class scatter matrix, not SBV. SBV is the between class scatter matrix computed using the vectors in the higher dimensional space. Now what I am telling here is M transpose SBV M. That is the between class scatter matrix computed using the vectors of our inner product matrix. You got the point? Meaning I can directly compute this M transpose SBM. Meaning I will not compute, I'm sorry, SPV, right? I'm not computing SBV, then go for M, all those things. I will not do that. Directly I will get what? M transpose SPV M. How I get? I get it from this matrix, right? The first 3 columns of this matrix I will take. I calculate, I treat it as the vectors belonging to the class 1. The next 2 columns, I treat it as the vectors belonging to class 2. Simply I compute what? Between class scatter matrix and within class scatter matrix. They are the numerics. I mean, there is no, I'm not talking about this variable wise, right? Because I already defined that V1 transpose V1 is what? K of U1 comma U1, right? So say for example, this is nothing but K of Vn V2, right? So what I do, very simple, I construct an inner product matrix, and each element, this is the experiment you are going to do now. Each element of this matrix, right? You are going to find out the kernel functional values. That's it. The raw data is what? The raw data is or X or U. I think I used U. The raw data are U's, right? UN and, right? Yeah, here I have written correctly, right? Raw data are U, right? You are going to do that kernel function K of UN comma U2. Whatever given data, feature dimension space, you are doing a kernel operator on that, right? K of U1 comma U2 is directly what? VN transpose V2. Got it? So directly you are going to find out this matrix. This is the starting point of KLDA. KLDA starts with this. KLDA starts with constructing the inner product matrix using the kernel function. Got it? You are given use. Using use, you are going to find this matrix. Elements of these matrices are U1 comma U2, right? You got the point? So all the elements are going to be filled up with K's. K of U1 comma U1, K of U1 comma U2, 1 comma UN, like that. This particular example for 5 cross 5, first 3 columns you are going to treat it as vectors belonging to the class 1 and remaining 2 vectors belonging to this class 2. Depends upon, if you are given multiple classes, the first N1 vectors you have to treat it as belonging to what? Class 1, and then next followed by the next N2 belonging to class 2, and then followed by N3 belonging to class 3, and so on. This one I am telling it is for the 2 class. You got this point? Right? Yes. So once you get this between class scatter matrix and within class scatter matrix, that's what I have mentioned here. This one, right? M transpose SPV and M transpose SWVM can be viewed as the between class scatter matrix and within class scatter matrix computed using the columns of the matrix given above, right? This inner product matrix, right? So it is like that. So now what is that? You see that VR equal to phi of UR. So VI transpose VJ can be viewed as what? Phi of UI transpose and phi of UJ. That's what I said. You are going to replace everything with what? The kernel functions. I recollect what is our requirement. Recall that our requirement is to find out Z. But what you are going to do? You are going to find out U, right? Once you get this U, I can simply find out Z just by replacing M into U. That is the goal. I mean, that's what the key point here. We are actually finding out this U. That is the point, right? So that is the important thing. So once this matrices are computed, so I can actually find out what? This eigenvector E. Right? So what is SB phi? This one I am defining it as a SB phi, nothing special in it. M transpose SBV M is SB phi here. M transpose SWV M we call it as SW phi here. You have SBV is different. SBV, SWV, what are they? They are all the between class scatter matrix and within class scatter matrix computed using the vectors in the high dimension. Happy that you are clearly reflecting what I am telling, right? So what is SB phi and SW phi? They are all the, I'll be happy if you tell. Yeah, so it is the between class scatter matrix and within class scatter matrix computed using the, using the vectors, column vectors of the inner product matrix, right? So they are interrelated. This SB phi and SB V, they are actually interrelated. In fact, finding out this SB phi and SW phi is easy. I mean, that is what we do. We don't find SBV and SWV. We find only SB phi and SW phi. That is the key point. So once we find that SB phi and SW phi, we can find out the eigenvector. This we can compute E, right? E we can find out. E is nothing but in earlier case, E is, I guess I use that U, right? Because Z is what? M into U. Here I used E, so that's the problem, right? So I use again the same E, or otherwise you know that, right? So we are actually finding out what? See, you see that this expression. This is the place, right? So this is the place of U, right? The same expression only I have written here, but I used E here. Okay, so E and U are the same, right? So don't get confused. So once this E is known, then I can simply use what? M into E to get what? Z. Job over. Okay, you may again think, right? Okay, but what is that matrix M consist of? What is a matrix M consist of? Matrix M consists of what? The vectors actually in the higher dimensional space. Then you will ask me the question. See, you said phi is not needed, but now I am having that phi, right? But again, you see that, once Z is defined like, M into E, I already told how to project the arbitrary vector X, feature dimension, which is actually available in the feature dimension space. What are the steps? You have to compute this phi of X, which maps the vector to the higher dimension. Then what you do? You multiply with the eigenvector. This is just for converting into 1D. If I have multiple vectors, I can project with the individual eigenvectors. So this is the projection to 1D, right? So now one of the eigenvector is my Z, which I can replace with what? M into E whole transpose. We can write it as E transpose M transpose phi of X. Interestingly, this phi M transpose phi of X, what is that you are getting? What is M transpose phi of X? M transpose is, M is this. So tell me what is that M transpose phi of X? Element wise, it is going to get multiplied with what? Phi of X, right? I mean, phi of X1 transpose phi of X. Got it? Right? Right? And then what? Phi of X2 transpose phi of X. Got it? Right? Matrix times the vector. What does it mean? Right? So it is like that only. What I am really saying here is, still you don't want what? Still you don't want phi. That is the answer. That is the point what I want to highlight. Still you don't want phi. You want only again K. right? To summarize, I mean, whether you got the exact derivation or not, I don't know, but to some extent you got it, right? But I know that it is very difficult for the first time when you listen, it will be difficult to understand, but you know the overall idea what we have done. But one point what you have to understand here is the steps that you must know. That is very simple, right? So if you are given a data like this UN, what is the first step you do? The first step is to construct the matrix, this matrix. This is the first step, right? You have to construct this matrix. That is the first step. Got it? And then second step is you have to find out the eigenvector for this. I mean, eigenvalue, find out that eigenvectors corresponding to the significant eigenvalues, right? Got it? That's all. That are the only two steps, right? And those eigenvectors is here, right? So if that's all, it's job over. But if I want to map the arbitrary vector x, right? What is the steps you do? You don't need to use this phi of x and all, right? What you have to do? You have to simply construct the kernels k of x, comma u1, k of x, comma u2. These are all the data given to you, training data, right? K of x, comma u3, like that. K of x, comma un. These are all the vectors, right? Right? And we already got this E. Simply do E transpose this vector. You project it to 1D. This is only projecting for 1D. If you want to have multiple projections, you take the corresponding eigenvectors. This is one eigenvector I have chosen, right? If you take two eigenvectors, what you do? E1 transpose this, E2 transpose this. If I have three eigenvectors, E1 transpose this, E2 transpose this, E3 transpose this. How many eigenvectors you want, you can choose, depends upon the significant eigenvalues. I hope this is clear, right? Any doubt? So we have a break in between, or shall we continue? Yeah, so actually what we do here today, we will do this. Is that ready? I mean, in lab, is it ready, or with the MATLAB in all the systems? Right. So what we do quickly, right? Tomorrow I want to cover this linear regression, right? So today we will do this PCA, LD and KLDA, all the three, right? So what I am suggesting is, right, first I think it is there in that system, huh? That code. Whether you are given that printouts were given. Okay, can I get one book? So then I can ask you to see to the book itself. So we'll do this experiment 1, right? Experiment 1 is for PCA, right? So all the commands, whatever is written here is all from the scratch. I mean, I didn't use any toolbox. The main objective is to make you understand the concepts and see how really it behaves. That's the goal of the whole experiment, right? So what you see in the figure, right, the bottom one, sir, that PDF what I have sent, right, for this one is ready. So can you take it? I can show it on the screen. I mean, until then, I'll just tell you, you can see to this you can see to this first figure, right? The left side, it's not there. But in my mail, it is there, but no, it will take time. I don't want to waste that time. So until then, I will just orally tell left, right? So that is the vector, right? What you see here, this is the data, which is actually generated randomly, which follows this randomly, which follows this Gaussian distributed with the arbitrary covariance matrix, right? So you can see that the first step in the code, rand-n, I will give you the outline of the code, right? So very simple. Rand-n will generate you the Gaussian data, but what is the covariance matrix you get if I have rand-n of, you are from which place, madam? Here only, right? Rand-n of 2, 1000, right? So what is the nature of the covariance matrix you get for x, random vector x? I asked her. Okay. No, it's better. I'm asking someone, right? So, okay, right. It is not really, yeah, it is going to have this covariance matrix as a unit, right? Identity matrix. Okay. Then you have this covariance matrix, arbitrary covariance matrix I have written, right? So, which is going to have that 1.99, 0.991, right? So, that is the covariance matrix of the data after projection. I'm not for generating the data. For the arbitrary covariance matrix, if I want to generate the data, what I have to do is, I'm using the same variable x that is equal to E into diag. Diag is basically the diagonal matrix, right? Right? And I'm taking what? The square root of that. What is the diagonal elements consist of? It consists of the eigenvalues, right? Fine. But basically I'm using EIG, right? That will end up with eigenvalues only, right? It happens to be the variance, that is a different story. But I'm using this EIG, right? EIG of CX, that will end up with E, capital E as eigenvalues. And diag is the eigenvalues. And then what I'm doing, I'm taking this diag power of, right, square root of the diagonal elements, E into diag power of into X, right? So that will generate the data with arbitrary covariance matrix. For that, so now you see the figure, the left side, bottom, right, page number 49 left. This is the 2D Gaussian data with arbitrary covariance matrix. The covariance matrix of this data is 1.99, 0.991. That is what the data is, right? Now, what you have to is what? The transformation matrix is the suppose x, which converts into y. Got it? So here you are plotting this graph in the right hand side. What you see there is, this is the projection from 2D to 2D. That's what you see. Got it? What is in the right side, left side is the 2D data. What you see in the right side is also 2D data. What you see in the right side is also 2D data, but after rotation. It means that, right, in the this axis, now it is going to be the eigen axis. This is eigenvector 1, this is going to be the eigenvector 2. You got it? Thank you. Yeah, here. So what I am saying, this red color, right? So the axis for this red color is eigenvector. Got it? This way eigenvector, this way it is a eigenvector. You see that? It is basically the rotating the data, right? So you are so this is the maximum variance direction. In that direction, it has been what? Rotated, right? So now you can see that, what is it? You can see for the next, right? This is the original data, the range, right? You can see that range. This is what actually you want to see here, right? So what do you see? The top two, they are all the ranges for all. Range, you know what I told, right? Little earlier, the range for this x coordinates and y coordinates. You have a wide range for x and y in the top two, and bottom one, left one, you can see the range has been what? Reduced. The actual values is plotted, right? So the range, right? So the range, the minimum to maximum, that is what we say, the difference between this minimum to maximum, right? I mean, the difference, right? So that is actually reduced here. And then you can see that other data, you have the range, right, for this eigen, right? So it's like that. Okay. So what will happen if I project the data only with one eigenvector? You can see that it is the straight line. All the points are lying on the straight line on this red, right? You can compare this original data. Yeah, it is there at the top. This is the original data, and what is given in the bottom is the 1D projection. Do you see any difference? Big difference? No. Right? Small variations you are missing, fine, doesn't matter. Right? So you are converted this 2D to 1D, will be happy, right? So this concept actually you can do it for the higher dimension also. This is the first experiment you have to feel like, right, how that is really working, the dimensional reduction. The second one is this LDA. Yeah. Sir, actually this is the 2D data. This blue color is the 2D data. We are actually finding out the direction of, this is the maximum variance direction. And we are projecting all the points on that. After projection, this is the points actually what you are getting. And this is actually on the line, single line. And these variations you are missing. These variations you are missing, but doesn't matter. That's what. So, yeah. Yes. The reason for plotting that one is to ignore. Right? We are not using that. We projected the data in two eigenvectors, right? One is second eigenvectors. Exactly. Whatever the projected on that first eigenvector is, the range is almost 0, so I don't want it. So I projected it on E1, that range is good enough, I mean, to, yeah, here it is a line. Yes, sir. Right? You got it. So the next one is this LDA, right? So the same procedure, you are going to generate the data, right? So here it's very simple. Again, this x1, x2 here, label is important. So I am generating this x1 and x2 both, right? To indicate that is a data 1 and data 2, and computing this between class scatter matrix and within class scatter matrix here, and then finding out these eigenvectors and then projections, right? So you can see that SW inverse SB here, this point, right? Okay, P inverse SW into what? SB, and you get eigenvectors and then eigenvalues, and then you are projecting that, right? So once yeah, what's the results are not there here. Yeah, I think I copied twice, I guess. No, it's for different covariance matrix. Okay. So this is the data generated. Okay. So in this case, the data generated is of what? 2D, but with a label. Red is Gaussian data with a different mean and covariance matrix, and blue is also what? Gaussian data with a different mean vector and covariance matrix. Now what you do in the right hand side is, after applying this LDA, right? So that's what you are getting here after subjected to LDA, right? Got it? This is after subjected to LDA, and then if I project it on the single line for this eigenvector 1 and 2, right? Yeah. So what you see in the top is the projecting the data with a standard basis. Meaning, whatever we are having this data, right? This data, you project it here and projected it here, right? Like this. When I do this projection, what do you see here? This bottom, we get that overlapping of this red and blue. Good amount of overlapping is happening, right? But after LDA, you can see that the overlapping reduces. The range for blue and the range for red, we get separation. And this is for the eigenvector 2, still overlapping, that doesn't matter. I am going to use only that eigenvector 1, right? What you have to compare here is, here both are having overlapping, the raw data. But after applying this LDA, the overlapping reduces here for the eigenvector corresponding to the significant eigenvalue. And the next eigenvalue, when you consider the overlapping is actually increasing, doesn't matter, I'm not going to use it, right? So I am going to use only this as a projected data, right? But still it is not happy, right? You are not happy because it's not well separated. You see that KLDA. That's what you have to appreciate, right? So KLDA, what is that? and then eigenvectors, all those things. But the procedure is exactly the same. So when I do this, you can see that this is the raw data. What is the red is somewhere and blue is somewhere, right? Do you see that? Right? So this is the power of KLDA. Red comes in one point, all the reds. Actually, it is not a single point. All the reds are actually brought closer to each other and it is looking like a single point. And all the blues are looking in the left, right? And that is the power of this KLDA. Yeah, the fifth experiment I will explain tomorrow. I think today, I think the time will be sufficient, right? Half an hour is enough. It ends at 5 o'clock, right? What is the time? Okay, then I can take, how much time you need? Huh? Yeah. Break is okay, but okay, after break, I think I will cover one more topic, or you want to go to the lab? So actually, I thought of taking regression tomorrow, but you have another session also, no, sir? Okay, then no problem. So I think this one you can try today after this, so that we can interact also, right? So every steps and all, any doubts if you have, you can get it clarified after the break. That will be better, right? So you can hold it. Basically, what I want you to understand here is the importance of dimensionality reduction. That is the key point, right? So once you know this, because this is not only the three techniques, right? We have, PCA, LDA, KLDA is most important, but we have something like ICA. I am revealing that, okay, fine, but this is independent component analysis, right? So maybe those who are working with CDMA, right? So you have that, suppose if I have NOMA, for example, if I have this mixtures of signals, if I want to get back your original signal, right? Original signals, and if I have additive noise is one component, right? If I want to remove that noise and then getting this individual component, I can use this ICA, independent component analysis, which is actually popular, very popular in music applications and image processing applications, where, for example, two speakers are talking simultaneously. See, suppose that in a dice, right? So I'm having microphone here, another speaker nearby, and we have a microphone to the next speaker, right? Both are recording my voice, and suppose that we are talking simultaneously, a part of his voice also gets recorded here, and part of my voice will get recorded here. It is basically the linear combinations of two sources, right? So using these mixtures, I can get these two separate, right? This is possible. This is basically two steps involved in it. The first step is this PCA. We do PCA first step. PCA does the job of making the covariance matrix diagonal, right? And then ICA means that it becomes the data uncorrelated. That is what PCA does. ICA tries to make the data independent. Independent is different from uncorrelated. I hope you know, right? Uncorrelated means what? Expectation of xy minus expectation of x into expectation of y, that is equal to 0. Independent means what? If I am able to represent the density function, joint density function as what? The product of the individual marginal density function, we call that as independent, right? We can even make the data independent, possible. PCA does the data uncorrelated. One step ahead, but for doing ICA, we have to do PCA followed by ICA to make the data independent. It's possible, right? So that's what I'm telling. Latent variable analysis in general, everything grouped together, right? So where you can appreciate, right? So why this dimension reduction technique is, after all, on various objectives we do that. KLD is having a different objective. ICA is having a different objective. Like that, still the list goes, right? So with this, I think I'll stop here. We have a break, and then you can do this exercise, and we'll discuss during the time, right? And I forgot to thank Professor for giving this opportunity for giving this lecture. Thank you very much, sir.